Hello everyone, welcome to Data Structures. Today we're going to talk about the Dijkstra algorithm that is used to find the shortest path from a node to every other node in a graph. Okay, so here in the example that you see we have graph G with 5 nodes, and we are going to find the shortest path between C and any other node. So the problem is finding the distance of C, the minimum distance of C to A, minimum distance of C to B, and to D, and also E. When we are talking about the distance, we are talking about the path. So we are not meaning like just a direct path. Sometimes there might be a direct path, like for example, you see between C and A, there is a direct path with cost 1, but there is no direct path from C to E. So there is no edges that are connecting these two nodes directly to each other. But definitely we can go from A to E, from using A we can go from C to E, or using D we can go to E from C. Okay, so now let's see how the Dijkstra algorithm works. So this algorithm is a greedy approach, is a greedy algorithm to find the shortest path. Okay, it means that at each iteration, at each step, it tries to find the minimum cost, okay, or use the minimum cost that it found so far. Okay, so let's say that like we have this cost associated with each edge. Okay, so for example, the cost between C and A is 1, but what we are going to do is associating a cost to every vertex. Okay, so I'm going to create an array, let's say an array C. Okay, that stands for cost, and I'm saying that for every vertex that I have, I'm setting the cost equal to infinities for every v with the little v belonging to the set of vertices. Okay, and this cost means that what's the cost of traveling from node C to any other node. Okay, so for example, we are saying that at first the cost of going C to A is equal to infinity. Okay, also from going C to itself. So what happens next is I'm gonna update the cost of C itself. So the cost of the node C, these two C's are different. Okay, so the cost of C, I'm gonna put it as 0, and also I'm putting the current node equal to C, so it's going to be number 0, and also I'm putting the current node equal to C. Now the Dijkstra algorithm says that go and choose the node or the vertex that has the minimum cost, and definitely because here we updated the cost of C equal to 0, it means that the cost of C going to itself is equal to 0, so we are choosing C. So I'm gonna put the value 0 here for C. Okay, now what I'm gonna do next is for every neighbor of C, for every direct neighbor of C that is B, A, and D, I'm gonna update the cost. Okay, so the cost is gonna be the minimum cost between their current cost, that for now is all of them have the infinity, they are all infinity, and the cost of the node that we are discussing, that is here is C, to those nodes using probably the edges that are connecting these nodes to each other. So the cost of A at first is let's do it in another color. Okay, so the cost for all of these things at first is infinity, 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 and here infinity. Okay, but so the cost of for A will be, I'm gonna update here, so let's change the color. So the cost of A, okay, it means that the cost of going from C to A is gonna be the minimum of its current cost, that is infinity so far, so and the weight from going from C to A, okay, C to A, plus the cost of C. That this is equal to the minimum of cost of A is equal to infinity, okay, so far is infinity, and the rate from C to A is equal to 1 plus the cost of C that is equal to 0. So together the minimum of infinity and 1 should be 1. Okay, so it means that the cost of going from C to A, okay, now will be updated to 1. So what I'm going to do is here update here this cost and update it to 1. So now the cost will be 1. So I'm going to do the same thing for all of the all of the neighbors of C that is going to be B and D. So C of B will be the minimum of like the current cost of B and the rate from going from C to B plus the cost that I have from C. Okay, so together let's write it here, and I'm gonna just write the final value. That's gonna be the cost of B. So far it was infinity. Now the cost of C is 0 plus the cost of C to B is gonna be 7. So the minimum will be 7. Now I'm going here and updating these, and I'm putting 7 here as the cost of, as the new cost of the B. Doing the same thing for D. So C of D, minimum of cost of D, and the weight from C to D, and whatever I had so far from C. So what's the cost of reaching C? That was 0. And the minimum definitely will be 2. Okay, so I'm dating here also and putting 2 here. So now what I'm going to do is finding the cost that is minimum. Okay, so we said that Dijkstra algorithm is a greedy approach. Okay, so first we started with C that had the minimum cost, and now between A, B, D and E we have to choose the one that has the minimum cost. Okay, so E is still is infinity because E is not the neighbor of C, so we haven't updated that one, so it's still infinity. And between A, B and D, A has definitely the shorter like the minimum cost. Okay, so we are gonna choose choose A, and also we are saying that A is visited. Okay, so we are checking C. Okay, so checking C as visited, it means we don't we want to like gonna update this information. Okay, now what I'm gonna do is I'm gonna see that what are the neighbors of A that we haven't visited yet. Okay, for every neighbor of A that is C and B, I'm gonna like calculate the cost. So I'm not gonna calculate C, okay, but I'm gonna calculate the A, okay, because we have the C visited. So the next is gonna be dating the cost of B. That's gonna be the minimum of the current cost of B, whatever it is, that is so far is 7. That means the from going C to B was 7, and the weight from okay A to B, okay, because now we are traveling from A to B, plus the cost that we had before for A, means that cost of traveling from C to A. So it's gonna be the cost of A. So the cost of B was 7, so it's gonna be the minimum of, I'm gonna write for the minimum of 7, and 1 plus 3, that's gonna be 4. So it means that now the new cost of B will be 4. So instead of going directly from C to B, that was 7, we can go from C to A, that cost 1, and then from A to B, that's going to be 3. So together going to be CAB, they're going to be cost 4. So I'm going to update the cost of B and put it equal to 4. So now also we are checking A as visited because we are done with A. Okay, so the cost from C to A is 1, and from C to B for so far is 4. Okay, now between the remaining nodes that are B, E, and D, we are going to choose the node that has the minimum cost. So definitely E is still infinity, so it's not a candidate, and between B and D, D has the minimum cost that is equal to 2. So what I'm going to do is I'm going to calculate the cost of B and E, okay, of the neighbors of D, and not C because C is already visited. So I'm going to like just to update and see that if I can update the cost of B and E or not. Okay, so here I'm going to update the cost of B. Okay, so it's gonna be the minimum of, okay, the current cost of B, that is 4 so far, or going from D, that is the weight of B and D, okay, B and D plus the cost that I have from like going from C to D, that is 2. Okay, so let's see, the current cost of B was 4, and going from the cost of B to D to B is going to be 5, and plus 2 is going to be 7. So it means that we are not going to update the cost of B, and the minimum is still 4. So that means that if we're going from C to B, okay, the best path so far is going from C to A and then A to B, and going from D to B is not a good candidate. Okay, so we are not adding that one. And the next one is cost of E, so we are going to update also that one. That's going to be the minimum of its current cost and the weight from D to E plus the cost that we have for D. Okay. So the cost of E was infinity so far. Now the cost of D to E is 7 plus the cost of D itself, that is 2, so together it's going to be 9. Okay, so now I'm going to update the cost of E and put it equal to 9. So here we'll have the cost 9. So we also updated the cost for E. Now we are checking D as visited. Okay, so far A, C, and D are visited. Now between those two remaining nodes that are B and E, we're going to see that which one has the minimum cost, that is B. B has the cost of 4 and E has the cost of 9. Okay, so we're going to update our current node. Okay, our current node will be B. Okay, and we are gonna update the cost of the neighbor of B. Okay, so we are not going to do this for A, C, and D. Okay, because they are the visited. We only know that it's remained as the neighbor of B is E. So the cost of E, okay, will be the minimum between its current cost, that is 9 so far, so C of E, or the weight from B to E, that is 1, and the cost that B itself has. So it means that the cost up to B, that is also 4. So together we'll have an update. It's gonna be 5. Okay, it means that for going from C to E, the minimum cost is going from B. That also for going to B, the minimum path was going from A. So the shortest path from C to E is from going C to A to B, and from B to A. Okay, so now I'm gonna update this 9 here and put it 5 here. So and then because there is no other neighbors that is unvisited, so I'm gonna check also B as visited. Okay, so B is visited, and the only node that is now remain is node E. Okay, so I'm with the cost 5. So it means that now I need to go and update the cost of neighbors of E, but the neighbors of E are B and D, both are visited, so it means that there is no need to do any changes, okay, because they are visited. So if you look at the cost, so C of E was 5, okay, C of B was 4, C of D was 2, and C of A also was 1. Okay, so as you see, the minimum cost of going from C to A is equal to 1, going to D is equal to 2, to B is equal to 4, that is going from A to B. Okay, and for E is 5, that is going from A to B, and C to A to B, and from B to E. Okay. Also, if you want to, that's like the Dijkstra algorithm. If you want to like know that what's the path. Okay, so here what we did is just finding the shortest path between node C and any other node. Okay, but if you want like to see that how you can also show the path or print the path, okay, what you can do is that whenever you are updating the cost of a node, okay, you can have another array that let's call this array, let's say previous. Okay, so it's a previous, and you can update the previous whenever you are updating the cost. So for example here for cost of E, okay, because now we are updated the cost that it was before was 9 and we updated to 5, so you can say that the previous node of E that in the path that I'm going to go from C to E is going to be. So here I can say that put the previous of E also equal to node B. Okay, so for any other updates I can do the same thing. Okay, as you remember, for example for A, the minimum cost caused by going directly from C to A. So the previous of node A was C. For D also was C. But for B, the minimum cost like between going from C directly or using A was going from A. So I can say that the previous of B is gonna be A. Okay, so and this way I can definitely just show the path. Okay, so the previous of, let's write it here, so the previous of E was B, the previous of B was A, okay, the previous of A was also C, and that's how you can show the path. Okay, so you first print E, okay, then the previous of E that is A, the previous of B that previous E that is B, previous of B that is A, and then also the previous A that is C. So that's the path, the shortest path from C to E. And for any other node, again, as I said, anytime that you're updating the cost for that node, if there's an update, then you are also updating the previous node for your current node that you are finding and updating the distance. So that's the Dijkstra algorithm to finding the shortest path, and as I said, it uses a greedy approach to find. So, and the greedy approach was on that part that it tried to find the cost that is minimum among all the remaining nodes that are not visited yet.